Okay, good afternoon, everybody. So we're talking about implementing a linked list. So the goals for today are showing you how to remove an element from the linked list, and then implementing the iterator. Now it's important that we review removing from the linked list because our iterator also needs to remove from a list. And so if we pay careful attention to how we implement remove in our linked list, then that makes implementing remove inside the iterator much easier. Okay, so I'm going to start by removing the front element from the list. There's no remove front method in our interface, but most linked list implementations provide this method, and it's because you can do this efficiently in a linked list. Right? So to remove at the front of a list, you can do that in O1 complexity compared to big O of n in an array-based list. Right? So to remove the front element of a list, it's just like dequeuing an element from a queue. Right? So to remove the 0 from this list, right, all I need to do is obtain a reference to this node because I need to return the 0. Right? And then update the head node so that it points at the second element or the second node in the sequence. Right? Of course, decrement the size of the list and then return the element that's in the removed node. Right? And so to remove the front element, ignore the, well, okay, so we'll start out with the special case. So if the list is empty, then you can't remove the front element. Right? Otherwise, get a reference to the current front element of the list. So that's just the head node. Right? Update the head node so that it points at the next element in the sequence. Right? So this head equals to remove next, or this head equals this head dot next. Either one is fine. There is a special case. Let's skip over that for a second. Right? Decrease the size of the list by 1, and then return the element that we in the node that we removed. And the node that we removed is called toRemove. Okay, now what about the special case? So if you're removing the first element of the list, then normally you only have to touch this dot front. Right? However, if the list has only one element in it to begin with, then you also have to adjust the tail node as well. Right? Because when you remove the only element from a list, you're also removing the tail node. So if the size of the list is 1, then you also remove the tail node, so you set the tail node to null. Right? And then away you go. So there's remove front. So that's relatively easy. Removing from the middle of the list, slightly harder. Right? So removing an element by index is similar to inserting an element by index. Right? If I want to remove that 2, then I need to do something to the node in front of it. Right? So I need to move to the node that's at index 1 or at index -1, right? To remove that element. Right? So the way we're going to do this is we're going to move to that node that's in front of the node we want to remove. Right? I need to hook n up to the one after the node that we're removing. So I need to I'm going to remember what toRemove is. Right? That's just n.next. And then I'm going to find the node after that. So that's just toRemove.next or n.next.next. Both work. Right? I'm going to unhook the node that I'm removing. Right? So I'm going to set its next field to null. And then I'm going to take n.next and join it up to the node after the one we just removed. Right? So one more time. Right? Move to the node that we want in front of the one we want to remove. Right? Remember what the next node is. Unhook the node that we want to remove. And then hook n up so that it points to after. Just like that. All right, finally decrement the size of the list and return the removed element. Right. So remove looks like this. Right. So if the index is, oh, wait. Move to, okay, so move to the node at index -1. So this doesn't work if index is 0 because we can't move to the node at index -1. Right. But that's what remove front is for. Right. So if I want to remove the head node, just call remove front instead. Right. So we have a special case here. Right? In general, if you want to remove the element at index 0, just call remove front instead. Right? Otherwise, check if the index is valid. Right? Move to the node in front of the one you want to remove, and then we're going to call remove after. So remove after is a private, it's a private method that removes the node after the node after node n. Right. Now the reason why I'm doing it this way is because in our iterator class, right, it's going to be useful to have remove after so that the iterator can efficiently remove an element from the list. Right. So notice remove uses move to. Right. So remove by index is in general in big O n because you have to move to the node that's in front of the node you're removing. Right. Remove after is in O1. So if you have an iterator that's sitting at some node and you want to remove the next node, then it's possible for the iterator to remove that node in O1 time. Right. Instead of calling remove by index, which takes big O n time. Okay, so remove after is just the pictures shown in the slide. Right? I want to remove the node that's after n. Right? So the one I'm removing is just n.next. Right? The node after the one I'm removing is just to remove.next or n.next.next. Right? I want to unhook the node that we're removing, so set its next link to null. Right? I want to set n so that it now links to the node after the one we removed. Right? So n next is now equal to after. Right? Decrease the size of the list by 1, and then return the element that was in the node that we just removed. Right? Now there's a special case. There's almost always a special case in these linked structures. Right? So there is a special case where the node that you're removing happens to be the last node in the sequence. Right? You know it's the last node if there's no node after the one that you just removed. Right? So if after is null, then we just remove the last node in the sequence. Because we're keeping track of the tail node in this implementation, right, we just remove the tail node. So we now have to make our reference this.tail refer to the new tail node. Right? And the new tail node is just n, right? The node in front of the one that we just removed. Right? So there's this special case that you have to take care of. Right? If you forget or neglect to take care of the special case and you happen to remove the last node in the sequence, the next time you call add, there's going to be a problem because you're going to end up adding to the wrong node. Right? So there's remove after. Right? If you count the number of operations, or if you look at the number of operations, it's just a bunch of assignments. Assignments and a condition. Right? So remove after runs in O1 time. All right, now that we have remove after, we're in position to implement the iterator. Okay, so just like in an array-based list, our model of the iterator is an object that sits between two elements. Right? So this iterator got to this position by calling next 1, 2, 3 times. Right? So at this point, if we remove an element, it's going to remove the C from the sequence. Right? If we call next again, it's going to move one position and return the D. Right? Okay, now in the previous implementation, we stored the indexes of the node, of the elements that the iterator was between. Right? So we had previous would be 2 and next would be 3. Right? You don't want to do that for a linked list. Right? So generally, you want to avoid index-based operations on a linked list, because the only way you can get to a node at a particular index is to start at the head node and then start following links. Right? So it's always ON for these index-based operations. Instead, what I want to do is I want to hold a reference to this node, right? And a reference to a second node. Right? With the array-based list, we kept this index and this index. Right? Now for a linked list, I want a reference to this node. I don't need a reference to the next node, though. Right? If I have a reference to this node, I can get to the next node just by following its link. Right? So I don't need a reference to that node. Instead, what I need is a reference to another node. Right? So I want to reference the previous node. So that was the node, or that holds the element that should be returned by next. Or sorry, that was returned by the most recent call to next. Right? So someone called next and they got the C, and now the iterator is at this position. Right? If I want to remove that element, right, then I need a reference to the node in front of it. right? And so for the linked list, we're going to keep a reference to the node previous, right? The node that's in front of previous, right? So we're not going to keep previous and next in this case. Right? So that node previous, that's the node that's going to be removed if we call the iterator's remove method. Right? To efficiently remove this node, I need to be at that node there, or I need to remember what this node is. Right? If I have previous, right, I can now call the linked list's remove after method to remove that node. Right? And that will occur in O1 time. So if you have an iterator on a linked list, you can remove an element from the linked list using the iterator in O1 time. Right? And that means that you can process the elements of a linked list one at a time and remove elements from the linked list. And you can do that for the entire list in ON time. Right? If you naively try to do that for an array-based list, you'll end up with ON squared time. Oop, there we go. Okay, so here's our iterator class. So our iterator class is called LL iterator, so the linked list iterator. Right? One of our fields is going to be the node previous. Right? So that's the node that's holding the element immediately before the iterator. Right? And then I want the node in front of previous, so that's previous. Ignore the constructor for now. I'll explain what's going to happen in just a second. Okay, so at the start of the iteration, there is no previous node. Right? So the iterator is at the start of the list. There's nothing in front of it. Right? Now, I want to avoid the case where I'm always checking, is the previous node null or not null? Right? So it would be nice if I could arrange things so that there was, in fact, always a node, that previous always, in fact, points at a node. Right? So I can play a trick. Right? So the constructor for the iterator can silently insert a new node into the list. Right? Now, the funny thing about this is that the linked list itself doesn't know this node exists. Right? Only the iterator knows that it's sneakily snuck in this node. Right? So I'm going to put in a node here. The only purpose of this node is to ensure that previous is never null. Right? So in other words, previous is always valid. I don't have to keep on checking it to see if it's null or not. Right? Now that node's not going to store any information. Right? So its element is just null. Right? But it does, in fact, point at the new head node, the head node of the actual list. Right? Now this node's called a sentinel node. Right? So it's a node that sits in front of the head node. Right? And its purpose is to ensure that there's always a node in the list itself. Right? You can also stick a sentinel node at the end so that there's always a tail node of the list. Right? If the tail node and the head node are both null, you have an empty list. Right? Or sorry, if the elements they're storing are both null, you have an empty list. Right? And in fact, you can implement an entire linked list this way. Right? So that where the linked list always has these sentinel nodes. Right? And if you do it that way, when you go and look at the methods that we implemented, you can get rid of most of the special cases that we have. Right. Okay, previous though can in fact be null. Right? So there's no reason that previous can't be null. So in our constructor, right, for the linked list iterator, we're going to sneak in a new node. Right? So we'll make a new node. Right? We'll store nothing in the node, but we'll make that node point at the new at the head of the list. Right? Previous can in fact be null, so that's fine. Okay, so what about has next? Right? So remember, our iterator has three methods: has next, next, and remove. Right? So has next returns true if there's more elements to visit. Right? Now, how do we know there's more elements to visit? Well, if previous is always a valid node, right, then if previous.next exists, right, there's some next element in the sequence. Right? So at the beginning of the iteration, right, previous.next points at the head, so there's something to visit, so has next returns true. When we get past the tail node of the sequence, right, so all the way at the end, right, notice previous is just the tail node, so previous.next is null. Right? And so now we have an easy way to check, or an easy way to implement has next. Right? Just look at the value of previous.next. Right? So if previous.next is not null, has next returns true. Right? So there's something in the sequence to visit. Okay, what about next? Right? So next advances are two references, previous and previous, previous, one position to the right. Right? So at this point here, if we call next on the iterator, right, the iterator moves one position to the right. It drags previous and previous, previous with it. Right? And then we return the element that's sitting in the node called previous. Right? So in this case, we're going to return the C. So next is easy to implement. Right? We're going to advance previous, previous, one position. Right? We're going to advance previous one position. Right? So this previous equals this previous dot next. Right? And then return the element that's in the new previous node. Right? Notice this line right here. If we didn't have the sentinel node, right, and this previous was null, that would throw an exception. Right? So if you don't have the sentinel node, you have to check is this dot previous null, right? And if it is, now you have to do something special, right? But because we have the sentinel node, we don't care about that anymore. The order in which you do this is important, right? You have to update previous, previous first, and then update previous second. Okay, so what about removing an element? So to remove any element except the first element in the sequence, right, you can just use remove after. Right? We've got previous, previous, right? So to remove the node previous, right, it's easy. You just call remove next. Remove after, and away you go. Right? There's a special case where you remove the head node, the first node of the list. Right? Okay, so after removing the node previous, you end up with the following. So if I remove that node right there, right, then we end up with the B is now linked to the D. Right? Previous, previous is this node here. Right? Now remember that in order for this iterator to work properly, the element in front of, the element immediately before the iterator is supposed to be called previous. Right? So that's easy to fix. Right? Just assign previous, previous to previous. Right? And set previous, previous to null. Right? Assigning that previous, previous to null is useful because it tells you someone has called remove after calling next. Right? And remember that the iterator contract for remove says that you can only call remove once for every call to next. Right? So after calling remove, we want some way to detect whether or not we can safely call remove again. Right? And so we can determine that if previous, previous is not null. Right? If it's not null, then we can call remove. If it is null, then we can't call remove. Right? Okay, so what about removing the first element of the list? Right? So now we run into a problem with our sentinel node. So if you call next once, and so if you start at the beginning of the list and you call next once, right, and then try to remove that node, you're removing the head node in the sequence. Right? So that's fine. We can just call remove front to remove the head node. Right? So if you call remove front, you end up with the following picture. Right? So the linked list adjusts the head node so that it points to the B, the second node. Right? Previous, previous both move forward one position. Right? So previous now refers to the A. Previous, previous is now the sentinel node. Right? But the head of the list is here. Right? And so what I need to do is I need to convert that node to a sentinel node. Right? And then ideally get rid of that node there. Right? So I can easily convert that to a sentinel node. Right? I just set the element to null. And now it's a sentinel node. Right? If I set previous, previous to null, right, that gets rid of the other node as well. That gets rid of the old sentinel node. So what does remove look like? It looks like the following. Right? So step one, can we safely call remove? So the answer is yes, as long as previous, previous is not null. Right? If it is null, then throw an exception. Right? Okay, now what about removing the head node? Right? So if the previous node is equal to the head node, so back here, right? So if previous is equal to the old head node, right? Then I know that I have to call remove front. Right? So call remove front, set the element in the previous node to null to turn it into a sentinel node. Right? If neither of these two cases are true, then I know that I'm calling remove after. Right? So remove the node after previous previous. Right? Update the previous node so it's now pointing at previous previous. Right? And then null out the previous node. Right? To indicate that we can't call remove again until somebody calls next. Right? When you call next, right? So when next is called, previous gets updated to a non-null node. Right? And there's the remove method for our linked list, for the linked list iterator. Right? And so the places where a linked list has superior computational performance compared to an array-based list is when you're doing stuff at the front of the list. Right? So if you remove from the front or insert at the front, right? In a linked list, it's O1 time. The other place where the linked list outperforms an array-based list is when you are iterating over the list and removing things conditionally. Right? So in other words, iterate over the list, look at the element, decide if you want to remove it. Right? In a linked list, when you call the iterator's remove method, right? All that ends up happening is you either remove from the front or you remove from an after node. Right? Both of those are O1. Right? So you can remove from the middle of a linked list in O1 time if you have an iterator in the appropriate position. Right? Even if you have an iterator in the appropriate position in an array-based list, right? That remove operation is ON. Right? So if you go back and look at the array list iterator implementation, all it does is call remove on the array list. And calling remove on the array list is always in ON. Right? And so that's the reason why there's two different list implementations in the standard library. You almost always want to use array list because get and set are O1. But if you're in the situation where you're doing stuff at the front of the list or frequently iterating over the list and removing stuff from it, the linked list may be a better choice computationally. Oh, there's no exam. There's an exam. These details are wrong. This is this is a recycled lecture slide. All right, so that's our linked list iterator. What do we do? Okay, so I now want to go back and look at array list and linked list and see if there's any methods that are missing from our implementation. So if we go back to our interface, so here's our simple list interface. Right? We've got size, is empty, add, get, set, add, remove. Right? What's missing? Right? So there's actually a bunch of stuff missing. So most lists should be able to, well, it'd be useful in Java anyway, if you can compare two lists for equality. Right? Similarly, it'd be nice if you could print a list or get the string representation of a list. Right? If you can test two lists for equality, you also need hash code. Right? So there are some important methods missing from our list interface. If you look at the Java standard library list interface, those methods are all there. So let's go into our array list and try to implement equals. Right? So how does this work? Right? So as always, right, when you override equals, it's always public Boolean equals object. Right? So it's always public, always returns true or false, it's always called equals, and its parameter is always big O object. Right? So it's not, right, that parameter is not sArrayList, it's not sList, right? It's always object. Right? So in any implementation of equals, you always do the same thing for the first few steps. Right? So if this equals obj, return true. Right? So the list and the object that we're testing for equality is the same object. Right? Step two, now we're in a situation where we have to ask, what can our array list be equal to? Right? So if we only want the array list to be equal to other array lists, right, then you use getClass. Right, so sArrayList can be equal to only another sArrayList. Right, so now you have to do the null and getClass check. Right, so if obj equals null, return false. Right, if this getClass equals obj getClass. I'm going to fix that in just a second. Not equal to. Right, so that's what you do if you want your array list, sArray list, to be only equal to other sArray lists. Right, so that's fine. Now you might say that, like, there's no reason an array list can't be equal to a linked list. Right, if you want to do that, you have to use instance of. So we'll come back to that in just a second. All right, so what's the next step? So the next step, if I get past this line here, is I need to cast obj to an sArrayList object. Right, so let's see what happens when we try to do that. sArrayList, so it's an array list of type E. Right, other equals cast. Oops, sorry, cast to obj. All right, so we do that, and Eclipse says there's something funny going on here. Right, so if you hover over this, it says, right, you have an unchecked cast from object to sArrayList E, right, which is fine. Right, so we'll keep on going with that. Okay, so now we've got other, right, and we can now compare the contents of our two lists. Right, so when are two lists equal? Right, so two lists are equal if they have the same size and the elements are in the same order, right? So if this size equals other size, or not equal to other size, return false. Right, now I want to test if their arrays are equal. Right, so return arrays equals this.arr. Whoa. And other AR. And away you go, right? All done. So that doesn't look too hard, right? All right, so that's not bad. Now, what happens if you want the alternative? So what happens if you want your array list to be equal to any other slist object? Right. Okay, so now things change. And you'll run into some complications along the way. Okay, so here is where sArrayList can be equal to can be equal to an slist. Right, now remember, slist is an interface, so let's see what happens when we try to do this. Right, so what I want to write is, so now I need to use instance of. Right, so I want to check. Whoa, sorry. Oh. Doop, boop, boo, not. So if obj is an instance of slist, return false. Right, that's what I want to write. Right, I want to check. Right, is slist, is obj, that thing I'm passing in, is it actually, or does it actually implement the slist E interface? Right, but notice that Eclipse is not happy with this. Right, there's a little red X here. And so if you hover over the error, it says, cannot perform instance of check against the parameterized type slist E. Right? So in other words, it's saying it can't check, is obj an instance of slist E here? Right? And it even gives you a suggestion. It says, change that to a question mark. Right? And now it's happy. Right? And so now the question is what on earth does that question mark mean? Right? And why is it a question mark? Right? And why is it not slist E? Right? So there's a whole bunch of questions here now that would be useful if you knew the answer to. Okay, so step one, what does the question mark mean as a generic type? right? So the question mark means the question mark means any type, right? Or I guess more specifically, some unspecified type. Right? Now that's not really what you want here. Right? What you really want is you really want to know, is the object you're comparing to, is it a list where the element type is of type E? Right? That's really what you want, but it doesn't work. Right? If you do that again, right, it complains. It says, I can't tell you if it's the element type, if it's a list of type E. Right? The reason it can't tell you if it's a list of type E, right, is because this check happens when the code runs, right? So it happens at runtime, right? The compiler isn't checking this, right? Because you can call equals with any object, right? And so the compiler doesn't know what's going to happen at runtime, right? And so why can't it determine if this is a list of type E? It's because the way generics are implemented in Java, at runtime, you don't actually know the generic type. Right? So in Java, you cannot, or not know right? So in other words, given a generic object at runtime, the virtual machine can't get the information of what is the generic type. Does not know the, sorry, this is not quite right. Does not know the type of does not know the generic. Right, so the virtual machine can't actually get the type of element that's in this list. That's not the way it works in Java. So in Java, what happens is the compiler is responsible for testing all of your generic types for type safety. Right? So in other words, the compiler ensures that if you make a list of integer, that you only put integer objects into that list. Right? At runtime, that generic type is erased. Right? So this is called erasure. Right? And so when the compiler compiles your program, it throws away all of the generic type information. Right? So your S list of integer at runtime just becomes an S list. Right? The generic type, all the type information is thrown away. Right? And you might wonder why the compiler does that. Right? And so the answer is because generics were introduced into the language in version 5 or 6, I don't remember what, of the language. Right? And so when they introduced this change, right, the language designers wanted to make sure that people's existing code, not just their existing written code, but their existing compiled code, would be compatible with the new version of the language. Right? Because at this point in time, there had been a lot of Java code written. So, right here. So the intention of the language designers was providing full source code compatibility and full bytecode compatibility. Bytecode is just the compiled Java code between different versions of the platform. Right? So this was the problem. So the problem was before they introduced generics, there was an ArrayList class. Right? So in other words, let me just go down here. Right? So you can write the following: ArrayList t equals new ArrayList. Sorry, let me just fix this line here so that I can get rid of the compiler errors. Oh wait, I have to return something. Return false. Okay, should be happier with that. Where? I'm not calling anything weird, right? No. There we go. Right. Okay, so this is going to complain. It doesn't know what ArrayList is, so I'm just going to import ArrayList. Okay, so now it's still complaining, right? It still says that, hey, array list is a raw type, right? You really should insert the generic type. But notice it's not an error. It's just a compiler warning, right? So in other words, you can in fact write this code, right? So I can add the string hello to that list, right? And that should go away. That's what? Oh, thank you. Awesome. Array list, let's call list. And then down here, what does this do? Like that, right? So the compiler is perfectly happy letting this happen, right? And the reason it's happy letting this happen is because the array list type before version 5 of the language was just array lists. There were no generics, right? Now, when they added generics, you're supposed to change this sort of thing, right? You're supposed to, when you make a list, you're supposed to write array list, blah, 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 blah. Array list string, list 2, new array list. So you're supposed to write that. Just like that, right? And now it's happy, right? List2.add, hello, right? So the problem is they could not change the language to force you to do this, right? Because the signature for this method, for the add method, for methods that involve this type, right, also involve the generic type name now, right? So the signature for these methods change to ArrayList E or T, the generic type, right? Whereas all the old code, the signature for all of their methods just involve ArrayList, right? The generic type doesn't appear, right? So the only way that they could change the language or add generics to the language without breaking everybody else's code is to throw away this type at runtime, right? And which is why back here, if you try to ask the compiler, or if you try to ask the compiler to compile this code, it complains, right? It says when this code runs, right, there's no way to actually know if the type of the array list element is E or not, right? So question mark it is, right? All right, this is also why you were never asked to implement this method in a lab or, well, you wouldn't normally be asked to implement this on an exam either, right? Because you would never get past this line. All right, so now we can get past this line, right? So now I can do the cast, right? So now I cast other. Right? So now I can attempt the cast, right? And now you have the problem of how do I test if the two lists are equal, right? So step one, the size still matters, so I can do that. Right, so that's still fine. Other, oh, it's not, right? Other size, right? So I don't know if there's a size field in the other object, right? Because all I know is that it's an S-list object, right? I don't know what type of S-list it is, right? But there is a size method, so I can fix that. So that's easy. Right? So that's no problem. Now, how do I compare the elements of the two lists? Right? Here, I just used arrays equals because I knew both lists had an array in them. Now, one of the lists the first list might be an array list, but I don't know what type the second list is, right? It might be an array list, it might be a linked list. Somebody else can come along and make their own list class and implement it in a totally different way, and I have no idea of knowing what's in that list, right? So how do you implement it?
I would assume you iterate through all the elements.
Yeah, you use an iterator, right? So you use a pair of iterators now, right? So iterator E, I1 equals this iterator, right? Iterator 2 equals the other iterator, Right? Now, why does that work? Because other is an slist object. Right? Guess what our slist interface has? It has an iterator method. So I can get an iterator over it. Right? And now what do? I just iterate over the two lists. Right? So while, now I know they're the same size, so I only have to check one of the two iterators, right? So while I1 has next, right? So I'm going to do E. Let's do it this way instead. Obj O1 equals I1 dot next, right? Object O2, I2 dot next, right? Test the two objects. If O1 equals O2, or if they're not equal, right, return false. That, right? If you get past the while loop, you've looked at all the elements in both lists and they all compare as equal, so now you can return true. Right? And you say, great, there's equals, right? And now you walk over to the other class, your linked list class that we just implemented. Right? And you say, well, let's implement equals for the linked list as well. Very long class, sorry. Split. Oh, hang on, let me get rid of this. Okay, so what about equals here? Well, you just go back and look at array list. Save that, right? And you look at the implementation of the array list equals, right? You look at that and you say, well, there's nothing here that's specific to array lists, right? This is just stuff that's in every slist object. So you just copy this and plunk it in here. So get rid of all that, right? And no compiler errors. No, because the cast is the slist, right? And both classes implement the slist interface, right? So it's the exact same code, right? And now you say, well, if it's the exact same code, shouldn't this be somewhere else, right? Shouldn't it be somewhere common? What's it complaining about? Oh, yes, I got, this is the main method. Okay, so now you say, if it's common code, shouldn't it be somewhere else, right? So shouldn't we just put it somewhere else and just reuse the common code, right? So what's the only thing that's common between slist and what's it complaining about now? Oh, there's no list U, right? So what's common between these two pieces of code? Well, nothing except the interface itself, right? So we know about default methods. Why don't I just make equals a default method and stick it in the interface? So let's see what happens if we try to do that. Right, so in the interface, let's put in the default method. So public default Boolean, blah, 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 blah.
Drop the override.
The override doesn't matter. You can put it in if you want to, but it actually doesn't matter. Right? And in fact, there's an issue here. Oh, so this size, like that. Okay. So I told you that you can implement a default method in an interface as long as you only use the methods in the interface. So let's see, what are we doing here? Iterator, that's in the interface. Has next is part of the iterator, so that's fine. Next is part of the iterator, that's fine, right? You can also use methods defined in object. So equals is defined in object, so that's fine, right? There's no other method calls here. And so you say, well, this should work, but Eclipse is still complaining. Right, and if you look at the error message, it says a default method cannot override a method from java.lang.object. And now you say, well, that's annoying, right? This is where I want equals to be, because this is the only place that's common between our two classes. But the compiler is saying I can't override a method from object, right? And so now the question is why can't I override a method from object inside an interface? And the answer is, why can't default methods override equals hashcode and toString, right? And so the answer is is the way that the language resolves which version of the method it needs to call. Right? So if you have a method in an interface and you have a method in the class, you have a default method in an interface, right? And you have a method that's found in a class somewhere, right? Then the method that takes precedence is the method that's defined in the class, right? So if your interface has a method called equals, which ours does, right? You have to ask the question, is there another class that also has equals in it? And if there is, that version of the method is going to take precedence, right? So which class defines equals? Well, object defines equals, right? Every interface requires an implementing class, right? So there must be some class that implements the interface. That class is a subclass of object, so it already has an equals method, right? It gets the equals method from object. And so that method there, even if it's here, would never be used, right? You're always going to get the version from object instead. So you can't implement a default method by overriding one of the object methods in the language, right? And so trying to do the sensible thing, putting common code into a common place, doesn't work in this particular case, right? So we have to excise that. Out it goes, right? And we're left with duplicated implementations in sArrayList and sLinked list. Yep.
Would there be a time when you could put it into a standardized part?
Yes. So that's the question. So it's software. You can always insert extra stuff, right? So how would you put this into a common place? There's a way to do this. Right? So what's common between our two classes right now? Right? The only thing is the interface, right? Can I insert a common class for these two? Right? You can make an abstract base class for these two classes and stick it there. Yep. Now it doesn't really make sense here because normally an abstract class is used when you have fields that are common and methods that are common. Here we only have a method that's common. We also have equals and hash code. They're all common. So in fact, it would not be a bad idea to insert an abstract base class here, right? So stick in an abstract slist class, put in all of your object methods, so toString, equals, and hash code, because they all have the exact same implementation, right? And then inherit from the abstract base class, right? And then you get the overridden equals, hash code, and equals for free. Right. Interestingly, it's not the way the standard library does it. The standard library splits the linked list and array list into two separate classes. But you can poke around in the source code if you want to see how it does it. All right, that's it for today. Next week, I guess, we're going to, this whole thing here where you have to use, where to go? Where did the question mark go? Here it is, right? This whole business with the question mark leads into a whole bunch of other questions when you're using generics. And so we'll take a look at what those other questions are in the next lecture. All right, I'll see you on Tuesday.